All right, indeterminate forms and L'Hopital's rule, which I believe we had talked about. You studied a little bit last year. Okay, so L'Hopital's rule is used when you're attempting to find a limit, and the limit results in an indeterminate form. Okay, so indeterminate forms, 0 over 0, infinity over infinity, infinity minus infinity, 0 times infinity, 0 to the 0 power, 1 raised to the power of infinity, and infinity raised to the 0 power. Sorry, guys. Only when these indeterminate forms result can we use L'Hopital's rule. All right, and I'll give a reminder of what that is. But just so you're aware, determinate forms are infinity plus infinity. And that limit approaches infinity. So if direct substitution, if you get a negative infinity minus infinity, then that limit approaches negative infinity. If you get 0 raised to the power of infinity, that limit approaches 0. And 0 raised to the power of negative infinity, that limit approaches infinity. Okay, so L'Hopital's rule. If you attempt to take the limit as x approaches c of f of x divided by g of x, and your indeterminate form results in 0 over 0 or infinity over infinity, and really any variation of this last one. So negative infinity over infinity, infinity over negative infinity, or when you have negative infinity divided by negative infinity. Then L'Hopital's rule says to evaluate the limit, you can take the limit as x approaches c of f prime of x divided by g prime of x. And this is not the power, or this is not the quotient rule, rather. This is just the derivative of the function in the numerator divided by the derivative of the function in the denominator, and then you reevaluate the limit. Okay, so limit as x approaches 1, arctan of x minus pi over 4, all divided by x minus 1. Now you do have to make sure that you get the appropriate indeterminate form, because if you don't, we have to rearrange it. So arctan of 1 is pi over 4 minus pi over 4. That would give us 0 over 0. So then we can use L'Hopital's. Limit as x approaches 1. Derivative of arctan of x, 1 over 1 plus x squared. Derivative of pi over 4 is 0. And then the derivative of the denominator is just 1. This becomes the limit as x approaches 1. So now we can do direct substitution. 1 divided by 2, so we get a limit of a half. It works even as we have a limit approaching infinity as well. So something as simple as x minus 6 over x squared plus 4x plus 7. Direct substitution would give you infinity over infinity. And we learned these shortcut rules. So I know that this function is bottom heavy, so this limit is going to approach 0. But just so you can see L'Hopital's, that would be 1 divided by 2x plus 4, derivative of the top over the derivative of the bottom. And now notice L'Hopital's doesn't apply anymore. All right, so it's not like you could derive the top and get a derivative of 0 divided by 2. It has to be one of those two indeterminate forms. So now when I go to evaluate the limit, okay, when x approaches infinity, I know that as my function gets bigger in the denominator, the limit will approach 0. So you can use it even when we don't really even need it. Okay, so now I have the limit as x approaches 0 from the right of x cubed times the cotangent of x. So a direct substitution would give me 0 times, and 0 from the right, that is a vertical asymptote on the cotangent function. So it would give me the indeterminate form of 0 times infinity. So as it's written, L'Hopital's does not apply yet. But we can rearrange this function so that we can get it in one of those forms. So limit as x approaches 0 from the right. So I'm going to write cotangent as 1 over the tangent, so I know that that works. As I approach 0, direct substitution would give me 0 over 0. So now let me take the derivative of the top, 3x squared. And then I'll take the derivative of the bottom. Derivative of tangent is secant squared. So now when I make a direct substitution of 0, I would get 0 divided by cosine of 0 is 1. So my limit is equal to 0. So even if it doesn't start in an indeterminate form of 0 over 0 or infinity over infinity, you can still get it in that form to apply L'Hopital's. All right, limit as x approaches infinity of x times the tangent of 1 over x. Okay, so direct substitution for this, it would give us infinity times, as x approaches infinity, this would approach 0. Tangent of 0 is 0. So again, indeterminate, but not one that we can go right to finding the derivative. Oh. Okay, so this method is used often. I know if I'm going to rearrange this. Well, I'm going to rearrange this. I'm going to say that multiplying by x, that's really the reciprocal of 1 over x. So I have the limit as x approaches infinity of the tangent of 1 over x divided by 1 over x. Now when I think about direct substitution, the limit as x approaches infinity of my numerator is 0, and the limit as x approaches infinity of the denominator would be 0. So now I have my indeterminate form. So now I can use L'Hopital's. Limit as x approaches infinity. This is your chain rule. Derivative of tangent is secant squared of 1 over x. Then derivative of 1 over x, that's x to the negative first. So negative 1, x to the negative second. Now my denominator, this again is x to the negative first power. So it's derivative negative 1, x to the negative second. These will cancel each other out. And now I get the limit as x approaches infinity. Secant squared of 1 over x. So as x approaches infinity, this will approach 0, and the secant of 0 is 1. So the limit of that function would be 1. All right, and last example. Limit as x approaches infinity, 1 plus 1 over x raised to the x power. Now I'm not sure if you did this last year, but we will talk about logarithmic differentiation if you didn't. So let's look at what direct substitution would give us. As x approaches infinity, 1 over x approaches 0. So I get 1 raised to the power of infinity. So it's an indeterminate form, but not one that we can just use L'Hopital's for. So I'm going to make this into an equation, and I'm going to say let y be this limit. And then what I'm going to do is I'm going to take the natural log of both sides of this function. And I can do that. It's an equation. So as long as I maintain balance, I'm going to rearrange it. So I have the natural log of y equals the limit as x approaches infinity. And I'll be taking the natural log of the expression. So the natural log will affect this, and then I know I can take the limit of whatever this natural log of this expression would be. So property of one of our log rules. Once I have the natural log, now I can bring this exponent out front. So I have x times the natural log of 1 plus 1 over x. Okay, so checking out if I have a proper indeterminate form yet, I would have infinity times, this approaches 0, natural log of 1 is 0, so infinity times 0, another indeterminate form, but another one that won't work yet. So now we have to continue to work with this. So I have the natural log of y equals the limit as x approaches infinity. So now I'm going to use that multiplying by x is really dividing by 1 over x. Okay, so let me put this on the next page. So I have the natural log of y equals the limit as x approaches infinity, natural log of 1 plus 1 over x, all divided by 1 over x. So now when I look at direct substitution, I get the natural log of 1 on the top, which is 0. The limit as x approaches infinity of 1 over x is 0. So now L'Hopital's will apply. So the natural log of y equals the limit as x approaches infinity. Derivative of natural log, 1 over the expression, times, now the derivative of the expression would be 0 plus x to the negative 1. So negative 1 x to the negative second power. Derivative of the bottom, negative 1 x to the negative second power. These will cancel. I get the limit as x approaches infinity of 1 over 1 plus 1 over x. This limit approaches 0, so I get the limit to be 1, but don't forget, we said y equals the limit. So right now we have the natural log of y is equal to 1. So to solve that for y, we know y would be e to the first power. So what does this represent? This represents limit as x approaches infinity of 1 plus 1 over x to the x power equals e. No additional homework for tonight.